All right, strap in, everyone. Today we're diving deep into the wild world of quantum mechanics,
Oh, yeah.
but with a philosophical twist. That's right, we're going to explore the mind-bending implications of this theory for our understanding of reality itself.
Cool.
To guide us, we'll be using the Stanford Encyclopedia of Philosophy's entry on quantum mechanics.
Right.
And today, we're not just skimming the surface. We're going for a deep dive into the math and the truly bizarre philosophical questions that it raises.
Absolutely. It's going to get weird.
So before we get lost in the quantum weeds, maybe we can set the stage a little bit. What exactly is quantum mechanics?
In the simplest terms, I guess you could say quantum mechanics is a set of rules for predicting how the tiniest particles in the universe behave.
Okay, I see.
Things like electrons and photons, the building blocks of everything.
Right.
And it's insanely successful at making those predictions.
So where's the mystery then? If it works so well, what's the problem?
The real mystery is not so much the math itself, but what that math tells us about the nature of reality.
Okay, I'm intrigued. Keep going.
Nice.
So this special mathematical language that quantum mechanics speaks, can you unpack that a bit more?
Sure. It all starts with the concept of physical systems, which could be, anything really, like from a single electron to the whole entire universe.
Wow, okay.
We describe these systems using their states, which basically captures everything we could possibly know about them.
Right.
And then there are physical quantities, the stuff we can actually measure, things like position, momentum, energy.
Okay, I'm following.
We call those observables.
Observables, all right.
Now, here's where things get really interesting. We have these things called state spaces. You can think of them like a map of all the possible states a system could be in.
So it's like if you could map out every single possibility.
Exactly. In classical physics, these state spaces are, pretty straightforward.
All right.
But in quantum mechanics, they have this much more intricate structure, and we call them Hilbert spaces.
Hilbert spaces. That sounds a little intimidating, honestly.
Yeah, maybe a little bit.
Could you maybe break it down for us, for those of us who aren't mathematicians?
Sure. Think of Hilbert space as a huge landscape, but it has its own unique geography.
Okay.
Understanding this space is like having a map to navigate the quantum world.
Right. I see. And the points on this map, the locations, they're represented by
Vectors.
vectors. Oh, like those arrows we used in high school geometry, right?
Exactly. Each vector represents a specific state that a quantum system could be in.
I see.
Just like in geometry, we can add vectors together, scale them, even measure the angle between them using something called an inner product.
Right. Okay. And why are these mathematical tools so important?
Well, they're essential for understanding how quantum states relate to each other.
Okay. Got it.
So, you see, Hilbert space is like a vast canvas where the drama of quantum mechanics unfolds.
I love that. That's a great image.
And these vectors, they give us a way to grasp how quantum systems actually behave.
All right. I'm with you so far. So we've got Hilbert space and these vectors, but then there's also this thing called a wave function, right?
Yeah, the wave function. It's a mathematical function that describes the state of a quantum system. Think of it like a blueprint.
The blueprint.
Okay, it tells us how much of each basis vector we need to combine to represent a specific state.
Okay. So it's like a recipe that tells you how to build a particular quantum state.
That's a good way to put it. So you see how these vectors and these bases and these wave functions all work together.
Yeah, it's all coming together, I think. But things get even more wild when we start talking about composite systems.
Oh, yeah.
Right. So what happens when we combine multiple quantum systems together? How does that change things?
That's where the tensor product comes in.
Tensor product. Okay, tell me more.
It's a mathematical rule that allows us to merge the Hilbert spaces of individual systems.
So we're basically combining the maps of the individual systems to create a map of the whole, right?
Right. But here's the mind-blowing part. Even if we know the exact states of each individual system,
Yeah.
the state of the combined system isn't always clear-cut.
Wait, hold on. How is that possible? It's like saying knowing all the ingredients doesn't tell you what the cake will taste like.
That's a fantastic analogy.
Is it? Okay, good.
It suggests that there are qualities that emerge from the interaction of the parts. Qualities that wouldn't exist if you just looked at the individual pieces on their own.
So the whole really can be greater than the sum of its parts in the quantum world.
Absolutely.
This has pretty big implications for our understanding of how reality works, wouldn't you say?
It definitely challenges our everyday intuition.
Yeah, it does. So what else does this quantum landscape have in store for us?
Well, to unlock the true mysteries of the quantum world, we need to talk about quantum operators.
Quantum operators. Okay, I'm ready.
These are mathematical entities that transform one vector in Hilbert space into another.
So they're like what? The architects of Hilbert space, shaping and reshaping the quantum landscape?
I like that, yeah. That's a great way to think about it. Now, among these operators, we have this special class called Hermitian operator.
Hermitian operators, all right.
And they're super important because they represent the physical quantities that we can measure, our observables.
Ah, okay.
Their eigenvalues represent the possible outcomes of those measurements.
Eigenvalues. I'm not sure I follow.
Let's say you're measuring the energy of a quantum system. The Hermitian operator that represents energy, it'll have a set of specific values, its eigenvalues.
Okay.
These eigenvalues correspond to the possible energy levels the system could have.
So the eigenvalues are like the allowed energy states for the system.
Precisely. And when we measure the system, we are basically forcing it to choose one of those allowed energy states.
I see, I think. So these operators, these eigenvalues, these measurements, they're all tied together.
They are. They're the keys to understanding the quantum world.
This is all very abstract, though. Got any examples?
Let's consider the hydrogen atom. It's one of the simplest atoms in the universe.
Yeah.
Now, the electron in a hydrogen atom can only exist in specific energy levels.
Right.
These levels are determined by the eigenvalues of the Hamiltonian operator, which represents the total energy of the atom.
Ah, so the Hamiltonian operator is like the rule book for the electron's energy.
Exactly. When we measure the hydrogen atom's energy, we always find it to be one of those specific allowed values, never anything in between.
So it's like the electron is playing a cosmic game of hopscotch, jumping between these predefined energy levels.
I like that. It's a great way to picture it.
Okay, so we have our Hilbert space, our vectors, our wave functions, and our operators. What's next in our quantum adventure?
Now we need to learn the rules of the game. And those rules, my friend, are laid down in something called the postulates.
Postulates. Okay, tell me more.
They're the fundamental principles of quantum mechanics, the bedrock on which the whole theory is built.
And they lead to some truly mind-boggling consequences, right? Consequences that challenge our whole understanding of reality.
Oh, absolutely. You have no idea.
All right, then, lead the way. Let's dive into those postulates and see what kind of philosophical rabbit holes they lead us down.
Let's do it. All right, so let's untangle these quantum postulates. The first one says that the state of a physical system, it's represented by a unit vector in Hilbert space. It's like giving a unique address to every possible state in our quantum city.
Okay, each point in Hilbert space is a distinct state the system could occupy. What's the second one about?
Second postulate, it dives into the heart of measurement. It states that any physical quantity that we can measure, our observables, are represented by a Hermitian operator in Hilbert space.
Okay, so these Hermitian operators, they're like tools that let us probe and measure specific properties of the system.
Exactly. And the possible outcomes of a measurement, those are given by the eigenvalues of that operator. Remember those specific energy levels in the hydrogen atom?
Yeah, those allowed energy states. I'm starting to get it. What about the third postulate? What does that one say?
That's where things get really interesting, at least from a philosophical point of view. It deals with composite systems, and it says that the Hilbert space of a combined system, well, it's formed by the tensor product of the Hilbert spaces of its individual parts.
So we're basically merging the maps of individual systems to create a map of the whole combined system.
That's the gist. But remember, we talked about this earlier, the state of the combined system isn't always completely determined by the states of its parts. This suggests that there might be properties, qualities that emerge from the interaction of the parts, properties that wouldn't exist if you just looked at the parts in isolation.
This really challenges our everyday intuition, doesn't it? We normally think that the whole is just the sum of its parts.
Exactly. But quantum mechanics, it suggests that the whole can be so much more than the sum of its parts, that there are properties that emerge from the entanglement and interaction of the components. You know, it's kind of like saying that the properties of water, like its wetness, its ability to quench your thirst, you couldn't predict those just from knowing about hydrogen and oxygen atoms.
That's a great analogy. Yeah, I get that. So, these first three postulates lay out the basic structure of Hilbert space, how we measure things, and how we combine systems. What about the fourth postulate? What's that one all about?
All right, the fourth postulate, it tackles the dynamics of quantum systems, how they change over time. And most of the time, the evolution of a system is governed by the famous Schrödinger equation.
Oh, the Schrödinger equation, right?
It's a mathematical equation that describes how the wave function changes over time, smoothly, deterministically.
So if we know the initial state of the system and we know the forces that are acting on it, we can use the Schrödinger equation to predict its future state. Just like that.
Pretty much, yeah. It's like having a set of traffic laws that govern the movement of particles in our quantum city. But here's where things get a little tricky. This smooth, deterministic evolution, it only applies when we're not making measurements.
What do you mean? Like, what happens when we do make a measurement? Does the system just ignore the Schrödinger equation?
In a sense, yes. When we make a measurement, something really drastic happens. You see, the system state, which could be in a superposition of multiple states before the measurement, it suddenly collapses into just one of those states.
Superposition and collapse. Those are pretty big words. Can you explain what they mean in this context?
Sure. Think of a coin spinning in the air. Before it lands, it's in a superposition of both heads and tails. We can't know for sure which way it will land, but once it lands, it collapses into a definite state, either heads or tails.
Okay, I see. I think
It's the same with a quantum system. It can exist in a superposition of multiple states at the same time, but when we measure it, it collapses into a definite state.
so. It's like the act of measurement is forcing the system to choose one path from all the possibilities. Does this mean that reality itself is fuzzy, indeterminate until we measure it?
That is a fantastic question, and it leads us to the heart of the measurement problem, maybe one of the most perplexing and debated issues in all of quantum mechanics.
The measurement problem, huh? Sounds like we were about to get into some serious philosophical territory. Tell me more. Tell me more.
The measurement problem arises from, well, it arises from this apparent conflict. The conflict between that smooth, deterministic evolution described by the Schrödinger equation and the sudden probabilistic collapse that happens during a measurement. This collapse, it isn't explicitly described by the Schrödinger equation. It's like this extra rule that we have to add to the theory just to explain what we observe.
So we have this really elegant mathematical framework. It beautifully describes the evolution of quantum systems. But then we need to add this extra rule, this collapse thing, just to account for what happens when we look at the system.
Exactly. And this raises so many questions. What actually triggers this collapse? Is it the interaction with the measuring device? Does it need a conscious observer? And if it does that mean consciousness plays a fundamental role in shaping reality?
Wow. Those are some deep questions, really deep. I mean, we're talking about the very nature of reality here. Observation, the role of the observer. Are we getting into metaphysics now?
I'd say we are. And this measurement problem, it's led to a whole bunch of interpretations of quantum mechanics. Each one offers a different perspective on how to make sense of this whole thing. You know, how to reconcile the math with what we actually experience.
So these interpretations are basically trying to answer the question, what does it all mean?
That's a great way to put it, yeah. They're trying to grapple with these implications of superposition and collapse, and the role of the observer. They're like different philosophical lenses to view the quantum world.
Okay, I'm definitely hooked. Let's dive into some of these interpretations. What kind of insights can they give us about the philosophical implications of all this quantum stuff? All right, so we've laid out this central mystery, this measurement problem, this head scratcher at the heart of quantum mechanics. It seems like we just can't escape these philosophical questions.
Yeah.
So let's dig into some of these interpretations. Where do we even begin?
Well, a good place to start might be the Copenhagen interpretation. It's historically the most prominent one, you know, the one that's still widely taught. It basically says that the collapse of the wave function during measurement, it's a real physical process, and that the quantum world is, well, it's fundamentally probabilistic.
So according to Copenhagen, when we make a measurement, we're forcing the system to pick a definite state from all those possibilities. But doesn't that just raise more questions, like what counts as a measurement? Does it need a conscious observer?
That's the big debate, right? The Copenhagen interpretation, it's a bit vague on those points. Some folks suggest that a measurement happens whenever a quantum system interacts with, with a macroscopic measuring device. Others, they lean towards the idea that consciousness itself plays a crucial role in collapsing the wave function.
Consciousness shaping reality.
Yeah.
That's a pretty wild idea.
Yeah.
It almost makes you think that old saying, if a tree falls in the forest and no one is around to hear it, does it make a sound? Maybe it's true.
It's definitely a challenging concept, philosophically speaking, but the Copenhagen interpretation, it leaves many of these questions open. It doesn't really give us all the answers.
Okay, so Copenhagen puts a lot of emphasis on the observer. and the act of measurement. What about other interpretations? Are there any that take a different approach?
Oh yeah, for sure. There's the many worlds interpretation. It goes in a completely different direction. It says forget about the collapse of the wave function. It just doesn't happen. Instead, every possible outcome of a measurement actually occurs, but in different branching universes.
Well, hold on. So instead of reality collapsing into a single state, it's like reality itself splits,
Yeah.
creating all these parallel universes, each with a different outcome. It's mind-blowing, but I guess it kind of sidesteps the measurement problem.
Right. Many worlds, it keeps that smooth deterministic evolution of the Schrödinger equation. No sudden collapse, no need to bring in a special role for the observer or consciousness. It's just that reality is constantly branching with every quantum event, creating this vast multiverse of possibilities.
A multiverse. It's like something out of science fiction. But doesn't it also create its own problems? Like if we can't access these other universes, how can we even say the multiverse is a real thing?
Yeah.
Can we even test it?
Yeah, that's a valid point. Many worlds has its critics, for sure. Some say it's not testable, while others find the idea of an infinite multiverse a bit too much to swallow.
So we have Copenhagen with its observer-dependent reality in many worlds, with its crazy multiverse. Are there any interpretations that try to stick a little closer to our single observable reality, something a bit more down to earth?
There are, yeah. Bohmian mechanics, also called pilot wave theory. It tries to bring back determinism to quantum mechanics. It does this by adding hidden variables that guide the paths of particles.
So instead of particles existing in this fuzzy cloud of probability, they actually have definite positions and momenta all the time, even when we're not looking. Sounds like it's going back to a more classical view of the world.
In some ways, yes, but there's a catch. The hidden variables in Bohmian mechanics, they're non-local, meaning they can influence particles instantaneously, even across vast distances, faster than the speed of light.
So even in this seemingly more deterministic interpretation, we still have some of that spookiness of quantum mechanics.
It seems that way, yeah. And, well, Bohmian mechanics has gained some traction lately, but it still has its fair share of criticisms. Some physicists argue that the non-locality is just as weird and counterintuitive as the probabilistic nature of the Copenhagen interpretation.
So it looks like we're left with this amazing puzzle.
Mm.
Quantum mechanics gives us this powerful mathematical framework for understanding the microscopic world. But it also leaves us with these profound philosophical questions about what's real, what measurement really means, and even maybe about the nature of consciousness. Is there even a right answer? Or are we just going to keep debating this forever?
You know, that's the beauty of it all, the beauty and the challenge of quantum mechanics. It forces us to confront the limits of our understanding and to wrestle with questions that go to the very heart of what it means to exist. Choosing between interpretations often comes down to your philosophical assumptions, what makes the most sense to you.
So it's like we're choosing our own adventure, our own path through this quantum landscape.
I like that. And that journey, well, it's just beginning. There's so much more to learn, to discover. And every new finding, every breakthrough, it's just going to spark even more philosophical debate, more wonder.
This has been quite a journey, for sure. Exploring Hilbert spaces, wrapping our heads around the measurement problem, even peeking into the multiverse. It's been a real roller coaster ride.
Yeah.
Any final thoughts for our listeners out there who are, philosophically inclined?
If quantum mechanics teaches us anything, it's that reality is much stranger, much more mysterious than we might have ever imagined. So never stop questioning, keep exploring, keep pushing the boundaries of what we think we know about the universe and our place in it.
Beautifully said. Thanks for joining us on this deep dive into the philosophical depths of quantum mechanics. Until next time, keep those minds open and keep wondering about the nature of reality.